Great. So I explained that this endomorphism of the antidotment project in the principle of the categorical can be identified with this co-invariant ring, which is the functions of functions on Q by the W invariant parts, the augmentation I do with W invariant parts, and by a well-known fact for cohomology of varieties. This is the cohomology. And so then how do you identify with the center? Here you need a theorem of Soergel, which says the following. So if you consider the function from the principal block to just module over this algebra, I'll just write it as C, given by just taking home with this antidotment projected. So this is in the literature you will see as factor B. So yeah, so normally I should write C off, but C the commuted rings are the matter. And the important fact is this functor is fully faithful on projected objects. That means if you take the subcategory of projected objects here, then it induces an equivalence of categories between the projectives and their input. And from this fact, you can show that the center, as we explained, well, it was an exercise in the first lecture, that the center is the same as the center of subcategory of projected objects in it. And since it's an equivalence, so this is the same as that. So this is the thing of the image of this category under functor B. But you see that the object C itself is in this category because it's the image of the antidotment projected. And therefore, actually, this is the same as the center of C, and but C is a computed ring. So therefore, we use this to identify the center of C, and hence we go cohomology of B. So this is the first instance of such identifications I discussed in the first lecture. And now I want to discuss the deformed version of this. And it turns out the deformed version is easier to establish. And then if time allows, at the end, I will discuss the relationship. So I want to discuss the form categorical and center. And the main idea behind this is the following fact from the community algebra that I'm use it all the time. So this basic fact is the following. So assume that R is an invariant just no invariant domain. And so M is an R module, which is called reflexive R module. That means if you take the dual of M with respect to R, so this check means you take home, and then reflection means M is naturally isomorphic to its double dual. So when you have a module with this property, then you can realize it in the following way. So we know K to be the fraction of R, and for any prime ideal.
Sorry, R commutative?
Commutative, yes. Okay. And if P is a prime ideal in R, then what we know by RP, the corresponding localization of RP. And then so you can do the following. So if M is reflexive, then it's proton free. So it embeds into its localization to K. So today I will not the following notation. If I write M sub K, that means I do M and then base change to K. So the same for RP.
Are all finally generated projectives like that?
Projective modules are reflexive, I think. Yes. Yeah, and then so you have this and embeds into it, and then actually as the subspace can be identified with the intersection of all its localization at P, such that you take the prime ideals of type 1. Okay. So this is the property of the reflexive harmonious. And now if you have now let's take A, which is an R integral free of finite. So over so in particular it's reflexive. And then now we want to study its center. So later you will think of your category O as modules over finite dimensional algebra. This is think of it as module over some algebra A like this. And you're going to discuss its center. And now you notice that the center of A, so it's just elements in A which commute with all the elements in AK. So this is the same as A intersection with the center of AK inside AK. But now you can replace A with this intersection. So this is the same as the intersection of finite ideals of type 1 of AK intersection with AK. But now this part is just the center of AK. So so then this becomes the intersection at type 1 finite ideals of center of AK. And everything inside the center of. So if you have so you have an algebra which is free of finite run over, then unit center is enough to know that it's centered at the generic point and also center at codimensional points. And so this is the main technique which makes the computation of deformed centered easy. But yeah, so we are going to basically work with the most often scenario which occurs is that you have a modular system. So you have let's say R will be some local ring, and then it's a regular local ring, whatever you want, and it's fraction field. So you have a fraction field, and then you have a residue field F. This is the residue field. And we'll be in a situation, so you have this algebra over R such that AK is fixed and simple. So then its center is very easy to compute. And what interests you is the center at and the residue field. So basically, this is the place you're interested in, and then you deform it. So then these are obtained by base train. And then you try to understand the generic and subgeneric situations to understand the center here. But I have a working, which is kind of important in this business, is that you have a surjective map like this. So it gives you a map from the center of AR to the center of AF. Because this is surjective. But this map is not necessarily surjective. It's not. So in general, it's not because you know the center of this deformed algebra, you could know the center of this algebra. But nevertheless, in some situations, it's okay. Right. And so now we want to put ourselves in such a situation where here you have an algebra at the beginning. And we want to introduce a deformed category which plays with the flow here. And we want to compute the center of that category. And the range we're going to work with is just filling this range would be one all time. So either you think of it as symmetric diagram of H or a function of the field. And since I want a local range, so I will take R to be the localization of S at the maximal ideal corresponding to 0. And I will denote by tau just the map from just the natural map from S on R. Given that it's localization map. But I can, so given tau, I can view tau as functions on H star with values in R. And now the definition of the deformed category is the following. So OR is defined as the category of both G insert R points. So this has a branch over C, and which is finitely generating, let's say, U equals unworking algebra, which is finitely generated over this unworking algebra, and then such that so n is the direct sum of weight spaces. And to simplify today, I'm just working with the integral. Here and the lambda to be inside this weight vector. But here what is n lambda? So n lambda is all the vectors in n such that if I have an action of an n h on it, it is equal to lambda plus tau evaluated h times n. So this is the place where it formed. Before, if we don't have R here, I would just have Hn is equal to lambda h times n. But now, since so n are modules over R, okay, so tau of h is an element in R, you can consider multiplication by those elements on n as well. And I impose this condition. And you see from here that if you specialize R to its residual field, that is repeating all non-trivial elements, then you just get back your weight space before. But yeah, but otherwise this is really the point where it's formed. And then the last condition is nx locally uniform. So this is as before. Definition of the category of multiple the G tensor R Mathas. And then you can define this as reversal reduce as before. So from now we do this instead of C use R and we let the height weight X this way as you use your value. And then you have projected modulus. So both of these are free over.
In the
Yes.
definition of the weight space, the quantifier is over all H in macro
Yes, it's for all H and H.
in H.
No, just in H. It's part of the EN.
We're viewing that inside of G, not inside of R, right?
Sorry?
You're viewing that inside of G, not inside of R, right?
Yes, like G, H inside of G, yes.
What is tau?
Tau is the step. So
Oh,
tau,
that H.
yes. It's, right, there's a confusion whether you just and that's not. The here is like the H. It's G, but tau is in R.
You said that you specialize tau, you covered the layer.
Yes.
Specialize tau zero or
If you specialize, so specialize means here you see, then yeah, then it's how it. Okay, and then the simple modules are actually simple modules in all practical modules. So some properties of this kind of, so first of all,
The weights are somehow we
it's contained in the finite generated. If you work with Categorification, then you're gonna need that. So there are some basic facts in finite dimensional algebra that if you have a finite dimensional algebra, then so if R is local, then this induces that the bijection between the blocks. So from that kind of idea, you can show that so I explained the block condition for all in a non-deformed case, but in a deformed case, you have a similar portion with W dot objects of O and R in such a way that if you specialize R to F, so here actually F input. This specialized to now I'm thinking. So this specialized to the blocking composition is different. And this each of the block, as we discussed, is equivalent to modulus over endomorphism of the projected. And now, yeah, there's something to prove, but you can show that this endomorphism space free R the finite exponent. I don't know the thing said it's actually free over R. And so this is really provides you an algebra like this. So yeah. So now we're interested to know the behavior of A and localization of your one. Okay, so now let's first look at the base range to refraction field. So now the claim is based on this language, the refraction field takes the this category is three semi-simple. So why is that? If you look at your so if you look at your central characters now, so your central character corresponds to well, if you maybe let me put it this way, if you now consider the Burma modules, okay, so the Burma modules of I space lambda and you base change it, okay, and then this lambda now corresponds to a character which is given as follows, is from, and it is given by sending an element x. So this is again, this is considered inside G. And it is given by sending it to lambda h plus anyway, lambda. So it's lambda h plus tau h. Okay. And now if you want to have non-trivial extension between Burma modules, it needs to have the same central character. Okay. But if you want chi of lambda, this is the central character correspondence, equals to chi of mu tilde. We have seen this is different only if it belongs to the same W dot objects. So mu tilde belongs to W dot of lambda tilde. Okay. That is, or in other words, mu tilde is equal to W dot lambda tilde for some W in W. But now, you look at these numbers, okay, but when you have that x on top of h, this is the embedding of h inside the symmetric algebra and then localized to R. And you know that h is a faithful representation of W. So if you have this, that means you have mu plus tau is equal to W dot lambda plus, let's say, a tau composed with W for W tau. Okay. But this is not possible unless W equals to 1. So this can happen only when W equals to 1.
Action W is not shifted. In action W and S of H.
It's shifted, but shifted it's on this part. So on this part there's no shift. Yeah. Okay. And so therefore from this you see that OK is actually the same symbol. And the simple objects is are just the Vermont modules and then the K. And their endomorphism is just K, so it's the same symbol.
Sorry, can we understand this as like using K as a recipient for characters just remembers everything about H? So that's why this like when our characters are valued in C, they can agree, but when they're valued in K, we just like separate it and use this representation.
Yeah, yeah. You can think of it that way.
Right, can you explain why did W dot totally determine whether or not to compare in O? Why was there not to check whether or not two things are the same power?
So if two things are not in the same W object, they don't have the same. This also
Okay, so over K. This is somehow not category. Is this? I'm on this.
okay. So this is this, and then the center of the center of this category is just, you know, if you have a semi-simple category, then the center is just, you have one copy of the field with simple objects. So it's the product when you want to be, there's a copy of the page for them. So now you look at you look at codimension 1 ideals, and they're actually for a reason which appear later on. There you only need to consider the following situations. And then the 2 is that you take for any positive roots. So let's denote alpha check the co-roots, which is an element in H. And then alpha check generates the height 1 ideal in S, which for an R, which I denoted by P alpha. And then we'll write R alpha just for the localization of R at this prime ideal. And here you just you invert all that elements which are not here. Okay, so you inverted all the other roots, for example. And then we'll denote by K alpha the residue for this. So in other words, if now you consider the map from S to K alpha, then you have mod out the elements in the direction of alpha check. But the other direction will be. So now if you consider the base change of OR alpha, so you first base change your O to OR, and then you can base change to this residue though. Then now you run the same kind of argument. So then now you have so now you run the tilde. I will think of it as element from H to this K alpha. And then now you run the same argument and look the tilde is equal to mu tilde. If not, it was. So you have the same condition here. Maybe there exists W such that mu plus tau equals to W dot lambda plus W compose with tau. But now you view it as elements in K alpha. So now you're allowed to mod alpha check. Because alpha check is specialized to because here if you apply W to some rendering stage, you so because here you basically because alpha check is goes to 0. Yeah.
So I'm still confused. How do we conclude that W equals to 1 on the left hand side?
Because here you basically require tau is basically you forget about R and think of it as an identity map inside S. And you're requiring for any H here, WH is equal to H as elements in S. No? Well, think of it as a polynomial ring. You're working in degree 1. And then you have WX on it. So if you have you have no other elements in W which can fix H because of the paper. It's a good exercise to think about.
I can't read the characters the length of the equal sign.
What?
On the last line.
Yeah.
It's the length of the equal sign. Yeah, and that very last figure.
Here.
Yeah, it's equal to W dot lambda plus W tau, what's the length of the equal sign? What's the second tau? Plus that's not right.
Yeah, now the thing is just you, maybe I should write tau alpha to be more precise. So here tau alpha refers to the map where it sends S to K. Then you want this to be the same, and yeah, okay, so if I write this, then I will need to write more about it. Okay, I'll write this. But now the thing is that so what can happen is just you now W can be one for the reflection with respect to alpha. Because those are the only elements which can produce you so on the H part, it will add in the reflection vector, which is in the direction of alpha check that is modeled in K alpha. So yeah, so this if this is the first time you see it, you will need some time to get used to it, but it's not difficult.
Why are we only looking at those specific type 1 ideas?
I would explain that later. So so then this tells you that W is equal to 1 or S alpha. So therefore, basically, this if you now consider the category O for this K alpha, then it will decompose into blocks, which are characterized now by P quotient by the dot action of the subgroup 1 and S alpha. Because only those things in the same S orbit can have extensions by this argument. And all the others they cannot. And so now if you so now you're this category can understand it very easily. So first of all, if lambda throw alpha check is 0, then P of R alpha. So then this category is again a simple way. So this is just because the S alpha dot lambda is the same as lambda itself. And so this is just given by the version of itself. Oh, sorry. So this is for K lambda, and then for the same reason as before, the block composition for R lambda, R alpha is the same. O lambda is this, and then you can compute. So if this is bigger than 0, well, I mean, one of them will be bigger. If it's not 0, then one. Then what you have is actually you recover a block which has the same structure as the block for SL2. So here you can compute the structure of the of this particular projective. It will have a filtration divergence like this. So if you go back to what we did for SL2 in the first lecture, you'll say things, and then this is the same as P and R. Okay, and then to understand the structure of this block, we want to compute this string. So it's the endomorphism of P and R alpha direct sum in P times G. Let's forget about the offset. Just do this, and this can be done quite explicitly. So actually, this is given by. So we have seen. Okay, maybe let me just write down the answer. So this is computed by the following figure. So each of the projected one item, one vertex in your figure. So you have like vertices or lambda, you have vertices for S of lambda. And then here you have the map from this projective to this one. So it's given by it's like this. And then you have another map, which is given as follows. So basically, you remember that. So if we were in a situation of SL2, what happens? So this is the anti-dominant. I have explained that it has the following structure. So now back to let's say over K over the field. What you have this is L of S of lambda, then L of lambda, and L of. And so you have the map. You have the map to first this quotient. So yeah. So in this case, this symbol is the verma, and so you can first map to the verma and then embed it back. So we have this maps to L and lambda, which is equal to M lambda, and this embedded the submodule into M lambda, which is P lambda. So you get a map over the residue field. You have the map like this, and it's called J prime. And then you can lift this map to this is a map between projectives. You can lift it to the projective over R. And this will give you this map, and moreover, you can lift it in so such that the composition, so J composed with N over the residue of the composition. And so you may live over however you want to put it. So it's in maximal ideal, and you can literally in such a way that this is alpha check times 7. And so this requires some work, but at the end result is like this. So now you have a very explicit equivalent, which is described for you this block, and you can compute its center. So to compute the center, well, you need to better understand this mechanisms, but that's hopefully have time to extend it, but it's not hard. So so this center if you constrain. So how you want to understand this center? You want to understand the subspace inside the center of AK, which is the product of all the over all the lambdas of the of A's. And therefore, you need to look at how your morphisms restricts to the verma modules, because this is the end of the verma modules. And at the end, the result is this. So this is all the elements in the product of R, such that you require that A lambda is congruent to S alpha dot lambda mod alpha check. For all, for just like this, for if lambda is not equal to S alpha. So therefore, okay. So now let me explain why you only need to consider such ideals. Because if you have a prime ideal like one which is not of this form, then its localization is still significant. So it's like it's already contained in the case. So this is only non-trivial, which produce the not only non-trivial hypermonic ideals will produce you different sense. And so now now you can just describe your center as the intersection of these things. So for example, now if we concentrate on the principal block, so now if we concentrate on principal block, then the vertices in O0 R are just the vertices which has a weight of the form W dot 0.
Oh, I can't read that relation. What's that? No,
Here,
yeah,
it's the composition, the relation of this, the composition of these maps, it's just multiplication by the m.
there's no relation to otherwise.
There's no relation. All right, and so therefore, if you look at this here, so as I explained, you just think of it as intersection, but it is zero this factor of O zero R alpha, or alpha belongs to plus inside the center of O zero A. But now you only have room, like the weights are inside this, so this is the product of elements in W of some properties of K, and then here you just consider the totals of elements with lambda perform W dot zero. So I just recorded them by AW for W belongs to W. Such that, so you ask AW dot zero is congruent to AX alpha dot zero. And so here you have AW is congruent to AXW on. And what is this range? This actually identifies with the invariant form for the diagram. And I just do a little bit on to explain this. So there's some big fact about bag variety. It will take some measurements. You haven't seen it, just ignore what I said. But it has in it, you know that you have an action of the particles on geometry. Then the fixed points are indexed by elements of the well group. And there's a one-dimensional object between two fixed points. So we can only if y is equal to some s alpha times x. And then so you have a one-dimensional of T object acting them, and the action is actually given by T functions by the T action is given by the character corresponding to alpha. So yeah, so among the characters I actually take the students. And then there's the description of equivariant cohomology of such varieties. That if you have a variety, fixed points are isolated, and there's only finitely one-dimensional objects. There's only a finitely one-dimensional objects between fixed points and with some extra connection on the characters which is satisfied in this case, then you can always describe the invariant homology in such situation where you identify this with the fixed points, the invariant homology of the fixed points. So this is just a bunch of equivariant homology of the points, which this is our S. So if I want this, I will need to, since I work with the localization side, complete this with respect to 0. And then the equivariant homology is described inside here as whenever you have a one-dimensional object, you impose this condition on the corresponding coefficients. So this is given by computing the cohomology of P1.
Why is it completed?
it's just on the representation side, I wanted things like working with R, which is sort of localization of this. It's like, you know, so I want to do the same thing on the cohomology.
It's not, it is not,
No, it's not localized.
oh. Oh,
Sorry. I don't know what's the that's the location. This. Okay, and so this is yeah, this is the thing about deformed category I want to talk about. And then in a deformed case, you can also identify O0R with the endomorphism of the antinomial projector. Because again, both sides can be computed using the same kinds of techniques. You localize K and then you things and you identify them. And now so let me just summary the so we have seen that the center of this deformed category is isomorphic to endomorphism of this weight, and it's isomorphic to invariant homomorphism of B. And now on the equivariant homology side, since this variety has only even homology, so this equivariant homology specializes well to the usual homology. So if you do the base change, the FC, you will get the usual homology of. And on the projective, also, if you specialize, you will get the angle of just taking the angle of projective commute with this. So here you will take just angle. And this remains to the end. But on the center side, as I said, so if you specialize, you do not necessarily get the, so you have, if you specialize, you get something like this, which maps to the center of OC, well, O0 in the beginning, but it's apparently not necessarily an isomorphism. But in this case, it is because we have shown that this is isomorphic to this. So it's because of this, this implies that this is an isomorphism. And then there are other situations which you don't. Well, it's not true. You can always go at the center as endomorphism of some projective. Very particular situation for the categorical, for the usual categorical. Like this. And this is also the thing why, you know, like outside of the category, if you want to work with parabolic, even like for parabolic categorical, there's no such isomorphism, and that is the difficulties many of your situations. Okay, I guess the time is up.